Word on this computer. Okay. Okay. Let's get started now with the next unit. Um, we're going to talk about concentrations and molarity, and eventually we're going to be doing our presentations. Okay, I've lost something. All right. Eventually, we're going to be looking at stoichiometry involving solutions. But for now, we have to talk about the general concept of solutions. The solvent is the component of a solution that most resembles the solution. Now, most of the time, we know which is the solvent and which is the solute. For example, if I dissolve table salt in a cup of water, it's pretty obvious. The salt is dissolving in the water, so the salt is the solute, and the water is the solvent. Uh, Sometimes it's pretty easy to tell. Very often, the the solute and the solvent might be in the same phase. For example, if I want to dissolve alcohol in water, which one is the alcohol and which one's the water, the solvent? Which one, well, if I take 10 milliliters of alcohol and put it into 90 milliliters of water, then I would expect the water to be the solvent. But how about if I took 10 milliliters of water and put it into 90 milliliters of alcohol? Then in that case, the alcohol is the solvent. Um, but the general rule is the solvent is the component that most resembles the solution. So if I looked at, for example, the density of the solution, whichever component had a density closest to the density of that solution would be the solvent. So we seldom have to make that critical distinction, but it is there, and that's the way we would define the solvent in solutions. Okay. We measure concentration of a solution by measuring the amount of solute dissolved in the solvent. And that's how we express concentration. The one that you have used all the time already is molarity. Now, molarity is the ratio of the number of moles of solute to the volume of solution. It is a ratio. If I'm saying I have 6 molar hydrochloric acid, what I mean is the amount of hydrochloric acid that I had is 6 moles divided by 1 liter, which gave me 6 moles per liter. So it is a ratio of two numbers. And you need to keep that in mind when you're doing problems with this. Yeah. So you have molarity as a ratio of two numbers. It's the number of moles of solute divided by the number of liters of solution. So remember, it is a ratio. Now, it doesn't really mean that a 6 molar solution has 6 moles of solute and 1 liter of solution. It's any two numbers that divide out to give you a 6. So um, remember, molarity is a ratio of two numbers. It's what you get when you divide the two numbers out. Now, if you cross multiply, you get a working relationship that's very important to us. The volume in liters times the molarity is the number of moles. If you do the unit analysis, you would see that. Molarity is number of moles divided by liters. So the liters would cancel out, and volume times molarity is moles. This is a very important working relationship that we will use in determining how much solute is present in a given volume of some molar solution. When you dilute a solvent, you just add water to it, so the amount of solute doesn't change. The number of moles of solute is still going to be the same after you put water in it. So we can take that relationship. I have a concentrated solution. If I take some volume of it and multiply it by its molarity, I can dilute it to a new volume and it'll have a new molarity, but the product of the two will still be the same. So we use this in mixing up solutions of a certain concentration that we might want to use in a reaction. So this would be the concentrated on the left side and the diluted sample on the right side. So we can solve for whatever we need to from that relationship. Whenever you dissolve some things in solution, it carries an electric current. We call those electrolytes. Current in a solution is always carried by the ions that's in the solution. So if you move the, if I put two electrodes in and into a solution to see if it carries a current, then if I have one of the electrodes positive, the other one negative, attached to a battery or something like that, to create a positive electrode and a negative electrode, the positive ion is going to move toward the negative electrode, and the negative ion is going to move toward the positive electrode. The opposite charges would attract each other. We use that sometimes to label the electrodes. The cation is the one that moves toward the cathode, and the anion is the one that moves toward the anode. And we use that to define the cathode and the anode in a cell, because cations are positive, so the cathode is negative. Anions are negative, so the anode is positive. That's how we put the names in. Now, you can't have free electrons in water. An electron is so tiny that when you put an electron into water, it will destroy the water. Every mole of electrons that you put into water would break the water molecules up, and you would have hydrogen gas bubbling off where that electron is going in at the negative electrode. And in that solution, that electron would release the hydrogen, but it would leave behind hydroxide. So if I put a negative ion into water, it's going to produce a negative ion inside the water, but it'll be the hydroxide ion. And that's what's going to move toward the other electrode in carrying a current. You cannot have electrons in water. They destroy the water. It's a process we call electrolysis. Now, when you put any ion into water, we've already discussed that ions are typically charged. They're charged either positive or negative, but we know that the water molecule has a permanent dipole moment. It has a negative part and a positive part. The negative part is around oxygen. Oxygen is more electronegative than hydrogen. So the oxygen part of the molecule is going to be negative, and the hydrogen end of the molecule is going to be positive. So when I put that water molecule in, the oxygen of the water molecule is negatively charged, so it's going to gather around cations in the solution and stick on rather tightly. So when you hydrate, when you put water molecules around an ion, it's going to increase its size. That'll weaken the force between those particles. So if I've got a cation and an anion, and I've got water surrounding both of them, they might not have enough attractive force anymore to come together and form a solid. They might just stay free in the solution and move from one place to another in the solution. And as they move, since the hydration increases the size. If you think about an ion moving in water, it's going to have to push out the rest of the water molecules as it's making its way over toward the electrode. And the bigger it is, the more molecules it has to push aside. And so it weakens the force holding them down, but it also slows the rate of migration and decreases the amount of current that ion is carrying across the solution. Now, when some species interact with water, the interaction is so strong that the compounds do dissolve in water. Again, if you think about the ions in water, they're going to be attracted to the water molecules. Let's go over and take a look at the pad. I'll illustrate what I'm talking about. If I've got a solid compound, it's going to have positive ions and negative ions stuck together in a three-dimensional pattern. I won't show all of it, but I'm showing the first two ions on the first row of the solid. Now, this ion is positive, so that means water molecules out here are going to come in and attach themselves right there to that water molecule. So what will, and other water molecules over here would do the same thing. They'll stick on to the water, to the cation, and pretty soon, the amount of energy that you put into forming all of these hydrations around this ion is enough to weaken the force between these others, and water molecules can now work their way on into the crystal, and the next thing you know, you just have that cation all out by itself, and water molecules attaching to it. And there's different numbers. One very common number, though, is 6. So some cations, for example, if I took copper plus 2 ions and put it into water, the copper plus 2 ions would wind up with 6 H2O molecules stuck to it. And if I go into the stock room to get a sample of copper chloride, say copper 2 chloride, I'm not going to find that compound in the stock room. What I'm going to find is the hexahydrate. And so now you've got these copper ions with 6 water molecules around them. That's still going to be in a solid. The chloride ions are going to be not a part of it. You're going to have the 6 water molecules attached to the chloride ion. And then in the crystal, the chlorides, the 2 chloride ions would still be in there, but they won't have water molecules around them in the crystal that you find in the stockroom. This is the one you're going to find. So whenever you put this into solution, you're going to have the copper ion hydrated, and that's going to stabilize it, and that's going to make it much, much easier for that compound to dissolve. So some species interact so strongly with water that the compound will actually dissolve in the water. Not everything does. We've learned the solubility rules in order to determine that. Now, you have to be careful about molecular compounds. When I talk about ionic species being some of them soluble, some of them not, we learned the solubility rules to determine what they were. But some molecular compounds dissolve too, but they don't create ions. For example, methyl alcohol, CH3OH, looks very much like water, really, molecularly. The only difference between the two is one of the hydrogens on water has been replaced with a CH3 group in methyl alcohol. So one end of the molecule, the OH part of that molecule, looks just very much like water, and it does dissolve in water, but it doesn't dissociate. It doesn't break apart into ions. So this compound, although it's soluble in water, would not be an electrolyte. It wouldn't carry an electric current. Now, let's look at a special class of compounds. It's called acids. Essentially, an acid is a compound that has the ion H3O plus in it. And generally, when we see formulas of acids, you're going to have compounds that look like this: the H and then some anion over here. One common acid we've already used in the lab a lot is HCl. Now, when you dissolve that acid into water, what you would get is an H plus ion and a Cl minus ion. And to show that they're hydrated in the solution, I can put a little AQ down here. That's what that aqueous means, actually, is the ion is aquated, or if it's not water, we'd call it solvated, but it's going to dissolve in water. And what happens then is actually, if I look at a water molecule, the water molecule has 2 lone pairs of electrons on the oxygen and a covalent bond to each of 2 hydrogen atoms in the molecule. Now, if I were to ask you, what is that line in that molecule? Well, you would say it's a pair of electrons. Well, you see, if I take this proton that I have up here, I can attach it onto one of these, and what I would get is that hydronium ion. The whole thing would carry the positive charge. Now, that is the reason why you can put something like a proton, and by the way, a proton and an electron are the same size physically. They generate the same kind of electric field. But electrons put into water destroy the water. Protons don't, because the proton has a place it can go to reside on the water molecule and make the H3O plus ion. Now, there are some other species in the solution, but essentially more water molecules attaching themselves to this cation. So you can have H3O plus, you can have H5O2 plus, you could have H7O3 plus, but the dominant species is this one. You're going to have more of that one, H3O plus, than anything else. So the water molecule can receive a proton and form the hydronium ion. And whenever you put any kind of acid into water. Okay, so this is the example I just showed you a moment ago. Now you notice this arrow just points in one direction, which means that this goes to completion in this molecule. If I put 1 mole of HCl into water and let it and stir it up and mix it, I won't have any HCl at all in the water. All I'm going to have is H3O plus and Cl minus ions. It'll be 100% dissociated. But you can't get free protons in water. You're not going to have really an H plus aqueous, although sometimes we write it like that to mean H3O plus aqueous, just to save ourselves some problems of writing those subscripts and superscripts every time. Now, I told you HCl completely dissolves in water and completely dissociates, but do all acids do that? And the answer is no. There are 6 strong acids that completely dissociate into water, and they are HCl, HBr, HI, HNO3, H2SO4, and HClO4. Now you need to memorize these because we're going to be interested in whether an acid separates or not when you put it into water. And we know these 6 do. If it's a compound that's got H in front, like this one, it's got an H in front and some anion beside it, like, for example, chloride or bromide or iodide or nitrate or sulfate or perchlorate, if it's got any other ion attached to it other than these 6, it won't separate. It isn't an electrolyte. It's what we would call a weak electrolyte. They will dissolve a little bit, but we need to distinguish them so that we can tell whether a particular acid dissolves or not. So if you see HX, it just means it's a weak electrolyte unless that X is chloride, bromide, iodide, nitrate, sulfate, or perchlorate. The others just partially dissociate in water. This will be extremely important in Gen Chem 2. Now, what about the topic was electrolytes. And we saw that strong acids are electrolytes. We saw earlier than that, soluble ionic compounds are strong electrolytes. Strong bases are also strong electrolytes. Now, they're pretty easy to identify because the strong bases on the periodic chart, the very first column on the left is group 1A, and the hydroxide of any one of them would be a strong base. It would separate into its ions. So, for example, if I put solid sodium hydroxide into water, it would break apart into sodium ions and hydroxide ions. It would be soluble. When we learned the solubility rules, it essentially said this. And when we learned nomenclature. For example, looking at the solubility rules for hydroxides, it says all hydroxides are insoluble except group 1A and group 2A. So these are the strong electrolytes. They do separate, so strong bases do. What if I had something like aluminum hydroxide? Well, aluminum's not in group 1 or group 2. So that means by the solubility rules, aluminum hydroxide, AlOH3, would not separate. It would stay as solid. If I put it into water, it would fall to the bottom of the test tube and be crystals and powder or whatever down in the bottom of the test tube. It wouldn't dissolve. So it would not be a strong electrolyte. So strong bases are. Weak bases, other hydroxides, are not strong electrolytes. Now, there is another one, though, that does a weak reaction with water, and probably the only weak base you'll encounter in Gen Chem 1 lab. It's ammonia. Ammonia has a formula of NH3. When you put it into water, it makes a little bit of NH4OH. So NH3 plus N. Let's go back over here. NH3 and H2O. Yeah, I'm going to do a double arrow here because it could actually go either way here, would make NH4 plus and OH minus. And of course, all these things would be aqueous. So this reaction will occur. You're probably going in this direction, maybe about 5%. So of the species that contain nitrogen in this solution, maybe 5% of those molecules are NH4+, but 95% of them would be NH3. So it doesn't dissolve much in water, but it does a little bit. It would be a weak electrolyte and would not be one of the strong electrolytes that we have. This is the only base that we're concerned about essentially in Gen Chem 1 or its lab. Okay. Now, a neutralization reaction is just the reaction of an acid and a base. When you react an acid and a base, you make a salt and water. This is a general reaction. Any acid with any base will completely react to form a salt. The salt is going to have the cation of the salt would come from the base. It'll be some metal hydroxide. The water would come from the acid H of the acid reacting with the hydroxide part of the base to make the water. So every kind of acid gives you this reaction. An acid and a base makes a salt and water. I've drawn the arrow only in one direction because it does go only in one direction. One of these will get used up. So if you add 1 mole of acid and less than 1 mole of base, you're going to use up all of the base. You'll have the salt and water, but you'll have a little bit of the acid left over when that happens. But this is the neutralization reaction. It is stoichiometric. Now, we write ionic equations to represent the things that are dissolved in the aqueous solution. Now, you don't write HCl aqueous. Why? Because it's not there. It doesn't exist. It's going to be H3O plus and Cl minus aqueous. So you would not show HCl stuck together in an equation unless you're talking about just a molecular equation. The ionic equation is going to have every HCl molecule broken apart into these two pieces. Now, there's an equation we call the net ionic equation, and you get that by adding two equations together. You're going to remove any ions that appear on both sides of the equation. So if I were to take some equation that had ions present and I break them apart, when I break all of them apart, all across that do break apart, that would be called the molecular equation, the ionic equation. When I cancel out the ions that appear exactly the same on the reactant side and the product side in the total ionic equation, if I cancel all them out, what's left is called the net ionic equation. And sort of an interesting sideline here is you can tell if a particular ionic equation, we call them double exchange reactions earlier, if the net ionic equation disappears, then there is no reaction at all. Okay, here's some problems that deal with this. What's the molarity of a solution made by adding 50 grams of aluminum nitrate to 500 milliliters volumetric flask and diluting to the mark? Now, let's see if I can stop the video, and I can't see my screen. So I'm going to go back to share screen. I have to be able to write that. I have to write the data down that we're using in this particular problem. Okay. We have 500 grams. I'm writing it over here on my pad, so you'll see it when we open up in a minute. 50 grams, I'm sorry, 50 grams of AlNO3 taken 3 times in a 500 milliliter of flask and diluting. And I want to know what is the concentration of, what is the molarity of AlNO3, 3 molarity of that. Okay, there we go. I've got the data collected and recorded. Let's stop screen share so I can get my pad back up over here. It's a little fuzzy, but maybe you can still see it. I'll change pins. By the way, we're going to finish. In fact, we're finishing just about now. We got such a late start. I'm not going to be able to finish this lecture in an hour. So what I'm going to do is I will continue recording, and then I'll upload the recording to D2L or a link to it so that you can watch the rest of it later if you want to. Okay, so we'll run out of time. Anytime you guys need to leave, go ahead. The recording will be up for you to view as soon as I can get it processed and uploaded. Okay, so we've got 50, we remind ourselves what molarity is. It's the number of moles of the solute. It's going to be aluminum nitrate divided by the number of liters of the solution. Okay. All right, now all we have to do is do the calculation to get the two numbers and plug them into this formula. All right. I had 50 grams of aluminum nitrate. Okay. Now, I need to convert that from grams of aluminum nitrate to moles. Okay. Now, so I want the moles of the aluminum nitrate. Well, if I had 1 mole, I can actually figure out how many grams that's going to be. So I'm going to get our periodic table over here. This compound has aluminum in it, and we have 1 aluminum. Aluminum is right there. You probably can't read it, but it's 26.98 grams. So that's 26.98. And I have to add then the number of nitrogens is 3. So I'm going to add to that 3 times the atomic weight of nitrogen, which on my periodic chart is 14.01. And I'm going to add to that the number of oxygens. That's 3 times 3 is 9. And the atomic weight of oxygen from the periodic chart is 16. So I'll do that on my calculator and report to you the number here. It's 26.98 plus 3 times 14.01 plus 9 times 16. That's 213.01. So I'm going to see my units are canceling out up here. So I'm going to go down here and say that 50.0 times 1 divided by 213.01. That's going to be the number of moles. Let's do that math. 50 divided by 213.01 is 0.2347, and there's just a whole bunch more digits there that I don't really need. And so now that's the number of moles that I'm going to plug back in to my formula up here at the top. Okay. Now, how many liters do we have? Well, it's 500 milliliters. So that's going to be 500 times 10 to the minus 3 liters. And this is the number I'm going to plug in also up here in my formula. And I can do the math. So I can do the molarity here. It's going to be equal to the number I have on my screen on the calculator now, divided by 500 with an exponent of minus 3. And if I do that, I get 0.46946, bunch of digits here, molar. That's the molarity that I'm predicting for this problem. So if I do a screen share, I can go over here and see that everything's okay. And we can follow through the solution here, just like I did. Here we go. That's the conversion of grams of aluminum nitrate to moles of aluminum nitrate. And we got this number. And then we take the volume of solution, that's 0.5 liters, or 500 times 10 to the minus 3. I divide these numbers out, and my answer is 0.469. And happily, that is the answer we got. Now, what volume of 6.5 molar what volume of 6.5 molar has 5.00 grams of nitrogen? All right, let's look at what we've got. We've got, I'm sorry, I misspoke a while ago. It's not grams of nitrogen, it's 5 moles of nitrogen. Okay, now we're going to do this as a unit conversion. We're given 5 moles of nitrogen. That's the amount and that's the unit. So I want to put moles of nitrogen in the denominator. And I noticed that in this formula, there's 3 moles of nitrogen in that compound. So that, and now I want to go to moles, okay? So when I do this math, I come out with, I would have canceled these out, but now I'm just going to string my factors together. And remember, I told you molarity was a ratio of 2 numbers. So I can convert from moles to liters just using the molarity. There's 6.5 moles of the aluminum nitrate in 1 liter of that solution. So when I do this, this would cancel out. And this would give me the volume in liters that would contain 5 moles of nitrogen. It's 0.256 liters, or 256 milliliters, depending on the way the problem is being reported. Here's another problem. What volume in milliliters of 6.5 molar aluminum nitrate has 1 gram of oxygen in it? Now look at this one and see if you can see that it is exactly the same as this problem up here in the way it's solved. What did I do up here? I started with an amount with a unit, and I did unit conversions after that. So I want to go from grams of oxygen, and looking at my formula, that's a 3. There's a 3 for the subscript of oxygen. So that's 16 oxygens. I'm sorry, 9 oxygens, and the atomic weight of oxygen is 16. So that 3 times 3 times 16 is the grams of oxygen in this compound, aluminum nitrate. And that would be in 1 mole. Now, that would get this canceled, but mole is not the unit of the answer. I want volume. So I'm going to do the same thing I did a while ago. I'm going to use the molarity as a conversion factor, set up in a way that the moles of aluminum nitrate cancel, and now can do this math. It's 1 divided by 3, and divided by 3, divided by 16, and divided by 6.5. And the ones up here we don't have to worry about. That's just multiplied by 1. So this is the number I get when I do this arithmetic. I get 0.00107 liters. Okay, or change it to milliliters if you wanted to. Here's another problem. What is the molarity of the resulting solution if 250 milliliters of 6.5 molar aluminum nitrate is mixed with 125 milliliters of 3.5 molar? Let's do some logic here and think about something. I'm mixing 2 solutions. One of them is 6.5 and the other is 3.5 molar. What do you think the relationship of the answer will be to these 2 numbers? Hey, I'm betting it's between the 2, right? We're going to mix them together. All right, so here we go. Molarity is moles per liter. And so I use that volume times molarity equals moles. Here's the volume of my 250 milliliters of 6.5 molar. Now, notice I did go to liters here. And this is the volume of the 3.5 molar, 0.125 liters. Now, that is the amount of solute that's present in that solution. I got solute from the first one plus the second one. What's the volume? Well, we're going to make the approximation that the volume is the sum of the 2. I had 250 milliliters of this one, that's 0.250 liters, and I had 125, that's 0.125 liters of this one. Now all I got to do is do the math. And I get 5.5 molar, and guess what? It did come out between the 2, didn't it? So if I'd made a mistake up here and got an answer that was less than 3.5 or greater than 6.5, I'd know those answers were wrong. Okay. And by the way, I want you to notice something else up here. I did convert these all to liters. I wouldn't have had to, because if I had 250 milliliters times 6.5 molar, that would be the number of millimoles. This would be millimoles, and the denominator would be in milliliters. So the millis would cancel out. I'm going to get the same answer that I got here for the concentration, as long as these units are all in the same volume unit. So we could have saved ourselves some time and some potential errors if we had just gone ahead and used these numbers as they were given. Number 5, what volume of water should be added to 255 milliliters of 6.5 molar silver aluminum nitrate in order to have a solution that has a molarity of 4.25 molar? Okay, let's set up our problem again as before. That's the definition. And the way we do a problem is we analyze the problem and see what relationship we need to solve the problem. And then we plug data into that relationship. All right, the volume then is going to be, we want 255 milliliters of 6.5, and the molarity that we want is 4.25. Remember, volume times molarity equals volume times molarity. I've just solved it for volume. It's 390 liters. or 0.390 liters, or 390 milliliters. Now it asks for the volume of water. So this is the total volume, 390. The volume of the aluminum nitrate solution was 255. I have to add a volume of water, and I can solve for it from this relationship. Volume of water would need to be 135 milliliters. There's checkpoints on these. I'll just pull them up here. You should work them out. They're really, really important because they're going to look like questions on quizzes and exams. So by all means, be sure you do these. If you have questions about them, put them on the discussion board, or if you are uncomfortable with that, I'll answer questions for you later if I need to. Now we're going to do solution stoichiometry, and the relationship that's going to allow us to do that is volume times molarity is moles. So let's work through some examples of this. What volume of 6.5 molar sodium hydroxide will react with 255 milliliters of 6.5 molar sulfuric acid? This is a reaction, so I'm thinking we do need to write the equation down, right? So we've analyzed, we saw we needed the equation. Now, the volume of the sulfuric acid is 255 milliliters of 5.65 molar. So there it is. So volume times molarity is moles. That's 1,441 millimoles if you multiply those out. Now let's look at the sodium hydroxide. We want to know, well, how many milliliters of this solution will we need? Well, we're going to first see how many millimoles we're going to need. The equation, we had sulfuric acid was 1,441 millimoles. The equation is showing 1,000 millimoles. That one is 1,000 millimoles, 1 mole. And this is going to be 2,000 millimoles. So now I've got the problem set up to work by the rebalancing method I showed you earlier. I can solve for this answer in millimoles by taking 1,441 and dividing by 1,000. That gives me my rebalancing factor. That's 1.441. My answer for the sodium hydroxide that we need is to multiply by 2,000. So 1.441, the rebalancing factor, times 2,000 from here. I get 2882 millimoles. So that's how many millimoles I need. Now, if I divide that by 6.5 millimoles per milliliter, that's the concentration. 6.50 molar is 6.50 millimoles per milliliter. And I did that to get this unit's the same. So I need 443 milliliters of solution. What about this one? What mass of copper is required to react with 50 milliliters of 6.5 molar nitric acid? All right. Again, we're going to need the equation. I didn't write the rest of the balance equation because these are the only two things involved in the problem. It's copper and nitric acid. The problem says what mass of copper, so I put a question mark with grams because it's asking for what mass is required to react with 50 milliliters of 6.5 molar. Now, to complete this part of the problem, this is in grams, so I want to show the 3 moles of copper in grams. 3 moles, copper's atomic weight is 63.55. So 3 times 63.55 is the mass of copper shown in this balanced equation. I have 50 milliliters of 6.5 moles per liter. That would be 327.5 millimoles. The equation is showing 8 moles or 8,000 millimoles. Remember, I got to get the same units. I could have used moles up here and moles down here. I'm just trying to be consistent with the way we set things up before. This defines our rebalancing factor. 50 times 6.5 divided by 8,000 gives me 0.04094 as the rebalancing factor. My answer now is going to be the rebalancing factor times what I've got under my question mark. That is 3 times 63.55, 7.81 grams. So this is the answer that I would get if I work this problem out the way we've done before. All we've added in doing solution stoichiometry is volume times molarity equals moles. How many moles of NO will form if 200 milliliters of 5.5 molar nitric acid is reacted with 25 grams of copper? Now again, we're going to set up the equation. I'm only showing the things in the balanced equation that are involved in this problem. And let's put our data in. It says we have 200 milliliters of 5.50 molar. That's 200 milliliters times 5.5 moles is 1,100 multiplied out, 1,100 millimoles. My equation is showing 8 moles or 8,000 millimoles. Over here, I have 25 grams of copper. The equation is showing 3 moles. The atomic weight of copper is 63. So the equation is showing 3 times 63.55 grams of copper. So I've got 2 rebalancing factors. This is going to be a limiting reagent problem. We want to know how many moles of NO is going to form. The equation is showing 2 moles. So let's do our 2 rebalancing factors. 1,100 divided by 8,000 is one of them. That's 0.1375. 25 divided by 3 divided by 63.55. That one is 0.1311. Now I compare these two, and this one is the smaller of the two. It's the limiting reagent rebalancing factor that I would use to multiply through the entire equation. But for this case, all I have to do is multiply it by what's under my question mark. And when I do that, I get 0.262 moles of NO. And that's the answer to my problem. If it asked grams, then I'd have I would have shown this up here in grams and still do exactly the same thing. I would take the rebalancing factor and multiply it by what was shown in grams. Okay, what mass of copper dissolved per milliliter in the solution produced in problem number 2 above? Well, let's flip through this. Now, I would get 7.81 grams. It would be in 50 milliliters. It's 156 grams per milliliter. Now, 0.156 grams per milliliter, that's a lot. But anyhow, I've put this up primarily because a lot of you are medical professionals, and the IVs that you prescribe for your patient is going to generally have the dose expressed in milligrams per milliliter. So you need to be able to convert what you get in the chemistry and solving for how much you want. You know, a patient weighs a certain number of grams. I'm telling you, you're going to have to express that in kilograms when you go to your physician handbook and look up how much of some compound you need to prescribe to a student or to a patient. That's going to be listed in milligrams per kilogram of body weight. So there's some conversions that you would have to do. And this is one of the problems you have to do, is determine the number of milligrams per milliliter you want to put in that IV bag so that it can be distributed to the patient over a 24-hour period at a certain drop rate. Sounds like a bit of math, doesn't it? Okay, if you're having problems with math, maybe you ought to think about a different major. Okay, here's your checkpoint. Now, this is a very difficult equation. It's one of the so-called 5 impossible equations to balance. No, it's not. I've modified this one, but it's similar to one of them. Okay. Now, problem you've got is what mass of chromium um, 3, chromium 3 oxide will be formed by the complete reaction of 1.5 grams of propane and 35 milliliters of 6.25 molar chromic acid. Okay, now remember, you don't have to go grams to moles, moles to moles, moles to grams. Please don't do that. It's waste time and you won't finish the exam or quiz coming up. Okay, practice until you've got the method I showed you down pat, and it will save you so much time when you get ready to work these kinds of problems. So remember the setup. I'm going to go in and put the amount of the materials given in the problem in the question. For example, I'm not going to work this one out for you, but what mass of chromium Cr2O3, I would go over here and over the 10 Cr2O3s in the balanced equation, I would put a question mark and grams. It's from 1.5 grams of propane. So I would go over the propane, the 3CH3C3H8 here, and I would write 1.5 grams up there. And then I would go 35 milliliters of 6.25 molar. Actually, what I would do here to make this easier is I would write that as 0.035 liters times 0.625 molar, and then I would show that in moles, and I would put under that the 20. So that would be a little quicker and easier. Okay? All right. Let's look at titrations. And when you are titrating things, you put one of the reactants in the burette, and you put the other one in the flask below. And this is the point of this week's experiment, I think. And so you read the initial volume. Your experiment doesn't require you to do this, but this is the quickest way. I've seen students waste lots and lots of time trying to fill the burette all the way up to 0. Look, we're only going to do the difference that comes out down here. So you don't have to start on 0, but you do have to record where you did start. And remember how to read a burette? You read it downward. See, there's 0, 1, 2, 3. That's the number of milliliters delivered. And then you look at where the meniscus is, and I'm saying that's reading 2.68 milliliters. It should have 2 decimal places. Now, this is what you do over here whenever you're done. And the way you know you're done is your indicator changes color. Maybe it's colorless over here. And when you get to a pink color, you know you're done. And so this is what the apparatus looks like when you finish the titration. You've added this much. Okay. And now we need to read this volume as well. This is going to be the final volume. Now, we want to make sure it doesn't go below the 50. If it goes below this mark, you're sunk. You got to go back again and start all over again, or be smart, go down to here, let it go all the way to 50, and you can calculate how much you put in that time. And then you could go back up here and fill the burette back up here, read that new initial volume, and then continue the titration until you do get pink, and then add the 2 volumes together if you needed to do that. Okay, so the volume delivered is 43.80 milliliters if you take this number and subtract that one. Now, I did this deliberately because when you do the subtraction on your calculator, it's going to show you 43.8. Do not report the data like that. This is a subtraction. You have to have the same number of decimal places in the answer that you used in the subtraction. You had 2 decimal places here and 2 decimal places here. The answer is to 2 decimal places. Record that 0. It won't show on your calculator when you do the subtraction. All right? Now there's 4 significant figures in this answer. So the equivalence point in a titration occurs when the correct stoichiometric of each reaction is put together. And there's nothing in excess. Everything's reacted. The reaction is essentially stopped. Everything's used up. But we can't always see the equivalence point in a titration. Generally, we get what is called an end point. And we do that by putting a dye, typically, into the flask in the reaction. And it'll have one color when I have that first reagent in it. And then it'll change colors and generally have a different color in it if I put what's in the burette directly into the flask. So what I want to do is keep adding the solution in the burette until I see a color change down below. Where the indicator changes color is what we call the end point in the titration. And it may not be the exact equivalence point, but if you choose your indicator properly, it'll be pretty close, okay? We want the end point and the equivalence point to be close to each other. All right, that completes the lesson for today. I will end the recording here, and I hope this will help you. If you're still with me, I appreciate your being here. I noticed that many people had to go. It's okay, but you can look for this video on D2L as soon as I get time to. It has to be converted and it has to be uploaded to Facebook, and then it's got to be downloaded again from there, or the link sent to D2L for you to use it. So that'll take me a little time to do that, but then after that's done, the video will be available to you. It will be available sometime soon.